Hello, class. Today we're going to talk about the different types of waves, how to identify characteristics of the wave, look at wave speed, and different behaviors. Very basics, though. So we're going to focus on traveling waves because that's the most common, and we are going to interact with behaviors of traveling waves. So what is the definition of traveling waves? Well, traveling waves definition are waves that transport energy without transporting matter. So particles within the wave are oscillating while the energy is being transferred. And that's specifically the case for things such as matter waves or mechanical waves, because they require a medium to pass through, and this is the medium of the particles that we're talking about. So this could be, water waves, earthquakes, like seismic waves, or even like sound waves with air particles, and all of those have the medium, whether it's water, the earth, air particles, so forth. But the other type of wave that we're eventually going to talk about more of, because it gets really interesting, is electromagnetic waves. They do not require a medium to pass through. They are oscillations of the electric field and magnetic field, and they propagate due to these changing electric and magnetic fields. This is somewhat connected when we talked about electromagnetism, because we recognize that a magnetic field is induced by a current, and a changing magnetic field can induce a current. Well, we know that it induces an EMF, which induces a current. And we know that that induced EMF is really an electric field. So the changing magnetic field is inducing a changing electric field, which is also producing a magnetic field, a changing magnetic field. So these two are kind of acting against each other, and there's no like friction to slow it down because there's no medium that it's passing through. It's just existing as in this space-time environment. Just gets a little bit more complex, but we just need to know that electromagnetic waves, which is light, is propagated by the oscillation of electric and magnetic fields. So if we were to look at the difference between the two, mechanical waves only oscillate back and forth, up and down, and energy is traveling as the particles are moving. In this case, the particles are moving up and down. Some are going to be moving side to side, and we'll look at that. Whereas a light wave has both an electric field vector and a magnetic field vector. And this red and blue lines represent the length of the vectors. The electromagnetic spectrum is quite wide, and we only really know it to be within our human eyes as the visible light. But the visible light is actually really small, only between about 400 and 700 nanometers of wavelength. But it expands out to radio waves, which is what we use to send signals across long distances, Wi-Fi, use it for our phones to send data, television, and microwaves, infrared, which we can observe the temperature of objects based off of that. More to come with that later. X-rays, which we use to do more accurate imaging of inside our bodies, but also even inside of luggage. It's pretty interesting when we get how that actually can occur. We will talk about that. And then all the way to gamma rays and higher frequency. We should also know, I think it's important to know that, and we'll see this. This is a frequency in hertz. This is the wavelength, and this is more energy, and this is less energy. So obviously X-rays and gamma rays could be damaging to us. That's why when you go into an X-ray machine, you have to wear this lead vest. Whereas obviously visible light isn't, and infrared isn't. Microwave and radio waves we use all the time, all around us. There's radio waves constantly traveling around us, sending data that we cannot observe. And those are less energetic, meaning they do not, they won't impact things as much. More to come with that later. So we're going to go back and really focus on mechanical waves, because those are the easiest for us to kind of make sense of in terms of particles moving, and it helps us understand the difference between the types of waves, transverse and longitudinal waves. So first, we want to just look at what type, how do the particles move in transverse waves. So look how the hand moves to make these particles move. You also want to focus on that little white thing in the middle that's moving up and down. Also, a longitudinal wave looks more like this. And you can watch how the blue string in the middle is moving through the slinky. So this is a wave as well, and the particles are moving differently. So how are they moving differently? Well, transverse waves have particles that move perpendicular to the wave's direction of motion. It's kind of hard to see sometimes, but this is the wave's direction of motion. So direction. If you were to, I would say, look at the top line or the top particles, and you can look and see like, oh yeah, that's like a water wave moving to the right. But these really all we look at is, oh, the particles are moving up and down or perpendicular to the direction of motion. Whereas a longitudinal wave, it's a little bit more trickier to see, but these are waves where the particles are moving parallel to the wave's direction of motion. So our wave's direction of motion, this one's a little bit easier to see this, wave direction of motion. And if we focus on one of those dots, look at those red dots, you can see them moving left to the right, to the left, and to the right. So we need to make sense of how this occurs, and also let's give the wave some characteristics to be able to understand or explain or describe how these types of traveling waves occur. So we have different characteristics of the wave. We have an amplitude, which we'll often call x naught, and this is very similar to simple harmonic motion, x naught. You'll also see it as like A, capital A, but I prefer x naught. Wavelength, which is our lambda, that's what we're going to use for wavelength. And we also have crests and troughs. And this wave, which looks kind of like a water wave, is the motion of a transverse wave as shown by the image of water on the top and the image of a graph below, where we have like it's moving up and down. These particles are moving up and down as they move to the right as well. This is kind of okay because we can see that if I were to kind of draw a where the equilibrium is, it would probably sit somewhere like right here, you know, and we can see particles that are either at the equilibrium position, or below, moving some distance below, 0.5 centimeters down. We could also kind of make a new one if I wanted to. Let's do maybe not orange, dark blue, yeah. Upward would be like a particle right here that's moved upward. Okay, that's easier to see. And this is not the hard one to look at. The hard one to look at is the longitudinal wave, because the longitudinal wave, it's kind of, we have to understand is where would the particles be if they were at equilibrium. So I'm going to plot this orange line, and let's imagine that all the particles were at equilibrium. And so if life is perfect, all the particles, let's say in air, actually let's not draw over the colored ones, all the ones in air would be like equally spaced apart, right? And then as a wave travels through this, so maybe like a sound wave, we have different pressure changes going on, and those are pushing the particles forward or backward. So if we looked at like this black dot, that matches with that black dot. But what about this dot right here? Well, if it were in its original equilibrium position, it would be right here, but it doesn't. It moves to in the negative direction, which in this case, right, this is negative direction, this is positive direction, because it's moving in the positive direction. So we can see that that particle right here, this red dot particle, is moving negative 0.5 centimeters backwards, or parallel to the direction of motion, but in the negative direction. We go to the next one, we see that the particle is sitting at equilibrium, no problem. If we go to this next black dot one right here, which I guess I'll do it in black, it's moved forward in the positive direction 0.5 centimeters. So where it was right here, it's now moved in the positive direction 0.5 centimeters, creating what's called a compression. And there we go, we've seen the center of compression, because this green dot is at equilibrium as shown right here. That's fine. And our blue dot, which is now this next point, has moved in the negative direction 0.5 centimeters. This is the blue dot right here. It's moved to the left 0.5 centimeters, and it's now sitting closer to the green particle that is at equilibrium. And so we have here this center of compression. We also call then, if we identify what compression is, that's a word that we might feel more comfortable with. What about, let's say, this part where there's not many particles because most of the particles have moved away from a compression? That's called a rarefaction. Just so some definitions we need to use. Okay, so those are the ways that we draw graphs about transverse and longitudinal waves. On a graph, they look the same, but in reality, the particles are either moving perpendicular to the direction of motion or parallel to the direction of motion in the positive or negative direction. Okay, now we've been looking at traveling waves, but let's give some more information about how to understand traveling waves. They're traveling, which means they must have a speed. So let's start with just looking at, again, these characteristics, identifying these characteristics, and looking at which ones help us understand how to find wave speed. So, of course, we have amplitude. That's not any different. And we said that's A or X naught. And this is just max displacement. And we can find this by either looking the maximum positive or maximum negative. It's just amplitude because it's like a sine wave. We have wavelength. And because it's a length, oh yeah, and this amplitude should be in meters. Because it's a length, let's do this. You know what? I need to fit. This is going to go over here. We know that this is meters. We call this lambda. It has the units in meters, centimeters. It's some distance. And this is the distance between two crests, which our crests are either the maximum displacement in the positive direction, whereas our trough is a negative displacement, negative maximum displacement. It could also be the distance between two crests, between two troughs, or even, if we wanted to, the distance between the beginning of an oscillation and when it reaches that same point on that oscillation. So this point, that's also a wavelength as well. Actually, why am I doing it in red? Let's do that in blue. The next characteristics we need to identify is the time period of a wave, which we call capital T, and we use the units of seconds. We have already done this in terms of simple harmonic motion with the time period of a pendulum or time period of a mass spring system. It is the time that one full oscillation occurs. We also have referenced frequency, and we use frequency to be 1 over time period. And the units for frequency is hertz, which is what we're going to kind of consistently use a lot more of when we start talking about electromagnetic waves, because we saw that frequency is proportional to the energy of a wave. That's going to come later. Now that we have this, these definitions of amplitude, wavelength, time period, frequency, right? This is frequency. It's actually right frequency. Let's see how they apply to wave speed. So there's two ways to determine wave speed. We are provided with a wave that is moving forward some displacement in some time value. And we can just say, well, you know what? I know my velocity is just equal to change in displacement over change in t, which in this case is change in x over change in t. It's the same. It's just that this graph shows a delta x for change in displacement. That could also work. We could also say, well, what if I want to find how long it takes for a wave to travel one full oscillation, like a time period? Well, how much time does it take for a wave to pass through one full oscillation? Time period, how much distance has it traveled? That's the same as doing wavelength over time period. Let's do that. That's just so this is just, how long does it pass through one whole wavelength? Well, it takes one time period to pass through one whole wavelength. So that's just equal to lambda over t. We also see this as lambda times frequency, because we know that frequency is equal to 1 over time period. So we're just substituting f into 1 over t. This equation will come up over and over and over and over. You might also see the symbol c work for velocity as well, because c is often often represents the velocity of a wave, specifically the velocity of an electromagnetic wave, or the speed of light. So let's give an example of how to solve for a velocity of a wave. In this case, we have a snapshot graph because time is technically stopped, and we can see the displacement versus position. We'll talk about that more next. And we can see particles on there, but we also notice that we can, since we have a position in the x-axis, that means we have the ability to measure wavelength when we only are looking at the graph. So let's try to determine where the wavelength starts and ends. And there's a lot of times we've said between two crests or two troughs, but I notice the crests and the troughs are not in the best place. But I do notice that if I were to start at the beginning and go to one full wavelength like this, I would end up with a wavelength of 25 meters. And so that is measurable because we notice that we have position in the x-axis. As the wave is traveling, I'm going to press play, and the wave is going to move forward. As the wave moves forward, we're going to look at these red particles, and we're going to notice that these red particles are going to move up and down. And in this case, it's showing kind of like what a transverse wave would happen, because we are seeing the particles move up and down, perpendicular to the direction of motion, which is going to be forward. As these particles move up and down, we need to measure the time that it takes for the particle to move up to the crest, down to the trough, and then back to its equilibrium position. So let's watch this, and the time is going to move forward. So first second, second second, third second, fourth second, hits at the crest, starts going down, passes through equilibrium, but that's a half of an oscillation, because then it still has to hit the trough, 15 seconds, and then it goes up to the equilibrium position, and that is one full oscillation when time equals 20 seconds. You can watch that again while I give the time period here as 20 seconds. We can see this and recognize that, hey, my frequency is 1/20 hertz, because hertz is 1 over seconds. And so I can use this equation for, okay, V is equal to lambda frequency, or lambda over T, and we get 25/20, and that's like meters per second, right? And that's like what, 0.125 meters per second, or 1.25. That's how long it takes for the wave to pass through a certain point, right? That's displacement over time, or wavelength over time period. I called this a snapshot graph, and now we need to actually identify what's the difference between a snapshot and a history graph is. And so the difference is, are we stopping time and looking at a amplitude or a displacement versus position, or versus distance? And this is going to be, again, of a transverse wave, where we're going to look at the red dot, and the red dot is going to move up and down perpendicular to the direction of motion. And then the history graph is exactly as it says. In order for history to occur, time must pass. So a history graph graphs based off of a specific point. So the history graph is looking at when does it pass through, when does the wave pass through a specific point in space. And so you'll notice this is the time behavior at x equals 10.25, which means, I need to zoom out, which means this right here, like if I were to, I can't draw on this graph, but maybe above, this distance is 10.25 meters. And as it passes through, it measures the vertical displacement as it goes up and down. So that is, let's insert some space so I can write here. This is a history graph. And in a history graph, we can measure time period, but not wavelength, right? If we paused right there and we looked at the graph, we can say how much time does it take for the particle to move up, down, and then up again, back to its equilibrium position. Whereas if we look at the at the snapshot graph, we're looking at a specific point in time. We can't measure time if we've stopped time and looked at it. And that is the snapshot of the wave at t equals 27 seconds. This is a little harder to see, but I want you to think of, okay, when does the graph pass 27 seconds? And you can use the left graph to see when it hits 27 seconds. And then the snapshot graph should match the image of the wave in the gray area. So let's wait until like, all right, it's 20, 25, 27. And then you'll see that that gray area graph matches the graph that's being snapshotted. It's like it stops time, takes a picture, and then that's the graph. And in that snapshot graph, like we just did above, since this has position, this can measure wavelength, but not time period, because we have like stop time. We've taken a snapshot of time, so we're not measuring time in that case. So you either need both of these graphs, or you need to be given one information to be able to determine the wave speed. I highly suggest going to my notes and going here to look at more advanced versions of this, or the same animations that I'm showing here. Okay, the last piece of information that I'm going to talk to you about is phase difference, and that is just how far off the wave is from another wave. A lot of times, if you have done this in math, you have seen this already, because you have like sine of theta plus, and then there's this is like a horizontal translation of the graph. How far to move it? Well, how do you move a wave horizontally so that it ends up matching itself with itself, and it must move a full period 2 pi. So if you do a full 2 pi, it's going back to itself. But what about in between 2 pi? And this is where we have this and this phase difference right here. The how far off it is that horizontal translation between itself. A lot of times, though, that's in math where you do a translation between itself. In this case, we're actually looking at two different waves and saying, what is the phase difference between these two different waves? Because they're all sine waves, they're all on a graph, and so forth. So if you have a phase shift of 0 degrees, this is like a phase difference of 0 degrees, that's like 0, or it could be 2 pi really if it's been moved over a complete oscillation. But generally this is right on top of it. So actually it better be 0. And this is like also 0 radians. And what about a phase shift of 90 degrees? And so you can see positive 90-degree phase shift right here. You can see that with B moving forward some amount of a period. In this case, if we look at it in terms of radians, right, we're looking at a pi over 2. We can also see this as or like lambda over 4 or time period over 4, depending on how you want to look at it. Or, yeah. So we're going to see it both in radians, meters, and seconds. The next one is also 90 degrees. It's just been moved backwards. So this moved backwards, or this has been moved forwards. So this is still negative pi over 2, or negative lambda over 4, or t over 4. These are all the same. They're just written differently, written in radians, meters, or seconds. And then if it's completely out of phase, where it's been moved completely over. Now, remember that a wave is ongoing, right? There's no such thing as parts of a wave. The wave goes from where it was emitted to where it has been received. And since generally when, where it's been emitted to where it's been received. And if it's a light wave, that happens instantaneously. So we don't really worry about these things. This 180 phase shift in degrees, or if it's in radians, it's pi, or lambda over 2, or like time over 2, how much it's off. So when we talk about the units, it can either be in radians, degrees, meters, or seconds. And like one full oscillation, what's a period for each of these? Well, for radians, 2 pi. For degrees, it's 360 degrees. For meters, well, it's just one whole wavelength. And for seconds, it's just one full time period. It depends on what it's asking for you. It's like, what's the phase difference in meters? What's the phase difference in radians? What's the phase difference? Well, they never really ask it of you in degrees. It's usually radians, and or meters. That's generally, but you might see also time period as well, or not even time period, sorry, time. All right, so if we kind of look at everything before I get to a practice problem, we've identified the two different types of waves we're going to talk about. I'll do a hint. We're mostly going to move towards electromagnetic waves once we get past these beginning of mechanical waves. We talked about how they oscillate, all the different types of EM waves, and then we really focus on what's the difference between transverse and longitudinal waves. Transverse being waves that have particles that moving perpendicular to the direction of motion, and longitudinal being waves that have particles parallel to the direction of motion. We showed how they would look in real life, and then how we draw it on a graph, knowing that the graph looks the same, but we need to know if it's a transverse or longitudinal and how the particles are moving. We've identified the characteristics of the wave. And in those characteristics, we found out we can find a wave speed, how fast it moves per unit time, how fast a point on the wave moves per unit time. It also works with longitudinal. I haven't showed this yet, but this is just a longitudinal wave traveling, where we can look at like the crests as compressions, and those are moving forward, while the particles are just moving back and forth, not actually being transferred. Just the energy of the wave is being transferred. And then we identified the speed and what kind of graphs or what kind of information we need to get to either wavelength, time period, speed, and so forth. And then we looked at phase differences, which we just talked about. All right, one practice problem before we move forward, and that is particles moving in longitudinal waves. And I already gave you kind of an answer. A sound wave of frequency 660 hertz passes through air. The variation of particle displacement with distance along the wave at one instance of time is shown below. State whether the wave is an example of a longitudinal or transverse. There is one word or two words in this question that helps you identify that it's longitudinal. And that is what I said earlier, and you'll need to know this. Longitudinal waves are waves that have particles moving parallel. So that could be sound waves, which it says this is. We also know this occurs in seismic waves, which are like earthquakes. And for transverse waves, these are, well, one, EM waves, so electromagnetic waves, light waves are transverse waves. We also say, I mean, not completely. It's like 75% transverse, but water waves kind of act that way. And actually, that's all we're going to talk about. And then I also have another question. Is this graph a snapshot graph or a history graph? We have displacement in the y-axis and displacement or distance or position in the x-axis, meaning we are looking at one instant of time. Well, how do we stop time to do that? This must be a snapshot graph, because we are stopping time or taking a picture of a wave at an instant in time. All right, part B is draw the displacement of the particles from their equilibrium position on the graph. In order to see this, it might be good to kind of say, hey, look, each of these is 0.25 centimeters between the dots. So it's almost as if these dots exist on this graph like this if the graph wasn't a wave, if they were all in equilibrium position. But since they are not, we have points on this graph that are in equilibrium position, and then we have points that move upward, and we have points that move downward. And remember, upward and downward just means positive and negative in terms of longitudinal. It actually doesn't mean up and down. It means forward in the direction of motion or backward in the opposite direction of motion. I want to make one adjustment to this, making this 1.5 millimeters, which is 0.15 centimeters. So negative 1.5 millimeters being negative 0.15 centimeters. And go ahead and pause this video if you'd like to work on this. I will show you the solutions in a few seconds. Okay, here it is where we see that the first blue particle is moved in the positive direction, 0.15 centimeters. So I moved it here. The first green particle has moved in the opposite direction, backwards, making a compression right here and a rarefaction right here. In this case, so remember, those black dots don't exist anymore. Those are the particles that I moved with the red and the green dots. The black dots have moved, and so forth. So that's it. All right, see you in class.